In the beginning, everything that exists, every star, planet, atom, and thought, compressed into a point smaller than the period ending this sentence, burning at 10 billion trillion degrees Celsius. Not hot in any way we understand heat. At these temperatures, the very fabric of reality becomes something else entirely, something we can describe mathematically but cannot truly comprehend. The birth happens in stages so brief that calling them moments seems generous. At 10 to the negative 43 seconds, the Planck time gravity tears away from the other forces, creating the first distinction in a previously unified cosmos. Before this instant, physics itself breaks down. Our equations return infinity. Our models collapse into mathematical nonsense. We stand at the edge of a cliff where all our knowledge simply ends. The temperature reaches 100 million billion degrees. But deeper questions remain. What exists at temperatures beyond this threshold? We have no physics that can describe it, no experiments that can test it. The first moment of creation remains forever hidden behind a barrier we may never cross. Then comes the inflation epoch, lasting from 10 to the negative 36 to 10 to the negative 32 seconds. A mysterious field, we call it the inflaton field. Though naming it doesn't mean we understand. It drives space to expand faster than light itself. Perfectly legal, physicists assure us, since it's space expanding, not objects moving through space. But what is this field? Where did it come from? Why did it exist at all? The universe grows by a factor of 10 to the 26th power in a time interval shorter than it takes light to cross a proton. Quantum fluctuations, tiny tremors in the fabric of space-time suddenly freeze and expand to cosmic scales. These ripples become the seeds of all future galaxies. Every cluster of stars, every void between them, traces back to quantum uncertainty, magnified beyond imagination. But here's what haunts cosmologists late at night. Inflation solves problems. It explains why the universe looks so uniform in all directions. It explains why space appears flat. It works beautifully in our mathematics. Yet we have no direct evidence it happened. No way to see past the cosmic microwave background to that first trillionth of a second. We infer inflation from its consequences, like detectives arriving at a crime scene billions of years after the fact. As inflation ends, the field's energy converts into particles, reheating the universe to 10 to the 27 degrees the Big Bang proper begins. But notice what we've just said. The Big Bang wasn't the beginning. It was what happened after inflation ended. The true beginning, if one exists, remains cloaked in mystery. Matter and antimatter wage the ultimate war of annihilation. For every particle of matter, a particle of antimatter appears. They meet. They destroy each other in flashes of pure energy. By all rights, the universe should have annihilated itself completely, leaving nothing but photons racing through empty space forever. But nature plays favorites. For every billion antimatter particles, there exist 1,000,000,001 matter particles, one extra particle of matter for every billion pairs. This tiny asymmetry, this cosmic accounting error of 1 part in a billion saves everything. Without it, you wouldn't exist. Earth wouldn't exist. Stars wouldn't exist. The universe becomes nothing but light. Why? Why does matter outnumber antimatter by precisely this amount? We have theories, we have models, we have no answer. The Sakharov conditions tell us what must have happened. Baryon number violation, C and CP violation, thermal non-equilibrium, but we don't know which specific process in the early universe created this imbalance. We don't know why the ratio is 1 in a billion rather than 1 in a trillion or 1 in a million. This mystery, one of the deepest in physics, explains why anything exists at all. By 1 second old, the universe has cooled to merely 10 billion degrees. Neutrons and protons have formed from quarks. The stage is set for the next act. In the next few minutes, nuclear fusion will forge the first atomic nuclei. The cosmic recipe is being written 75% hydrogen, 25% helium, and traces of lithium. These proportions persist in the oldest stars 13 billion years later. We find ancient stars born just a few 100 million years after the Big Bang, and their composition matches our predictions perfectly. This agreement gives us confidence. We understand what happened after the first second. The physics checks out. Our models work. But that first second, that realm of extreme energy where all force is unified, that remains beyond our grasp. Consider what we're really saying. The entire observable universe, 93 billion light-years across, containing 2 trillion galaxies, once fit into a region smaller than an atom. How is that possible? General relativity allows it mathematically, but can we truly claim to understand it? The density becomes infinite, the temperature becomes infinite, and infinities in physics usually mean our theories have reached their breaking point. String theory suggests the Big Bang might not be the beginning at all. Perhaps it's a transition, a bounce from a previous contracting phase. Perhaps our universe is one bubble in an eternal sea of universes, each beginning when quantum fluctuations in some parent space trigger inflation. Perhaps time itself emerged during the Big Bang, making questions about before is meaningless. We simply don't know. What we do know is this. 13.8 billion years ago, something extraordinary happened. Space, time, matter, and energy came into existence or underwent a dramatic transformation. The universe began expanding and hasn't stopped since. Everything we see, today, every star, every planet, every atom in your body traces its lineage back to that moment. But the moment itself, the very first instant, that remains shrouded in mystery, protected by physics we haven't yet discovered. We've pushed our understanding back to a trillionth of a trillionth of a trillionth of a second after the beginning. And there, at the very edge of comprehension, we find something remarkable. The limits of human knowledge marked not by lack of curiosity, but by the inherent opacity of nature itself. The Planck epoch, those first 10 to the negative 43 seconds, may remain forever beyond our reach. At those scales, quantum mechanics and gravity merge. Space-time itself becomes grainy, fluctuating, uncertain. Our 2 best theories of physics, quantum mechanics, and general relativity give contradictory answers. We need quantum gravity, a theory we haven't yet formulated, to describe what happened in that first moment. Several candidates exist. String theory replaces point particles with tiny vibrating strings. Loop quantum gravity quantizes spacetime itself into discrete chunks. Each theory makes different predictions about the Planck epoch. Each remains unproven, perhaps unprovable with current technology. And so we face a profound truth. The universe's opening chapter is written in a language we haven't yet learned to read. We know the story begins with unimaginable heat and density. We know what happened after the first second with remarkable precision. But that first second itself, when everything we see was forged, remains the greatest mystery in cosmology. Yet from this mysterious beginning, everything follows. The first atoms, the first stars, the first galaxies, all emerge through processes we can trace, calculate, and verify. The universe's history becomes increasingly clear as it ages. We can map cosmic evolution from 1 second onward with stunning accuracy. But deeper questions remain. Why does the universe to exist at all? Why these physical laws and not others? Why did inflation happen? Why does matter outnumber antimatter? These questions haunt the edges of cosmology, reminding us that for all we've learned, the universe still guards its deepest secrets. The first second that created forever gave us everything, and it gave us mysteries that may outlast the stars themselves. In the next chapters, we'll explore what emerged from this mysterious beginning, the long darkness, the first light, the formation of cosmic structures. But as we do, remember, everything rests on a foundation we can describe, but perhaps never fully understand. The universe began. How and why remain the ultimate questions. And perhaps that's exactly as it should be. Some mysteries don't diminish our understanding, they deepen it, reminding us that reality is stranger and more wonderful than we ever imagined. What we've discovered about the first second is extraordinary. What remains unknown might be even more so. For 180 million years after the Big Bang, absolute darkness reigns. No stars burn. No light shines anywhere in the cosmos, a darkness so complete that calling it black understates its totality. If you could somehow exist in this epoch, floating in the primordial hydrogen gas, you would see nothing, not the faint glow of distant objects, not even your hand in front of your face, nothing. This cosmic dark age stretches longer than the time since Earth's first complex life appeared, longer than the entire history of animals on our planet. 180 million years of absolute unbroken night. And yet, during this darkness, the universe prepares for everything that will follow. The temperature drops from 3000 Kelvin, hot enough to keep electrons separated from nuclei, to about 60 Kelvin, cold enough for hydrogen atoms to form and stay intact. The universe has become neutral, its particles no longer electrically charged, no longer interacting with light. Photons travel freely through space for the first time since the Big Bang, but there's nothing to see them by. No sources of light exist anywhere. What was happening during these missing ages? We have theories, we have simulations, but we have no photographs, no direct observations, no light that survived from this period to tell us the story. The cosmic dark age remains largely invisible to us, hidden not by distance but by the absence of light itself. Matter begins its slow dance of assembly. Gravity, weakest of the fundamental forces, but infinite in reach, pulls hydrogen and helium into gradually denser clouds. The process takes millions of years. Atoms drift through space, moving slightly faster toward regions of higher density, slightly slower away from them. Imperceptible changes, accumulating over geological timescales, building towards something momentous. But gravity doesn't work alone. Dark matter moves first, immune to radiation pressure that pushes normal matter around. These invisible particles, 5 times more abundant than the atoms that make up everything we see, create a cosmic web of filaments stretching across billions of light years. We cannot see dark matter. We cannot touch it. It doesn't interact with light at all. Yet it shapes everything. Think about that for a moment. The universe's structure, where galaxies form, where voids appear, the entire architecture of cosmic space is determined by something completely invisible. Dark matter creates gravitational wells, invisible valleys in space-time that trap normal matter like water collecting in geological depressions. Where dark matter concentrates, normal matter follows. Where dark matter is absent, vast voids remain empty even today. How do we know this if we can't see it? Computer simulations tell the story. When we model the universe with only normal matter, we get the wrong result. Galaxies don't form quickly enough. The cosmic web doesn't match observations, but add dark matter 5 times as much mass as normal matter, interacting only through gravity, and the simulation matches reality perfectly. The agreement is so precise, so detailed, that few physicists doubt dark matter's existence. Yet we don't know what it is. Not really. WIMP's weakly interacting massive particles remain a leading candidate. Axions, theoretical particles 1 trillion times lighter than electrons, offer another possibility. Primordial black holes formed in the first second might account for some dark matter, or perhaps it's something else entirely, something we haven't yet imagined. Experiments run deep underground, shielded from cosmic rays, waiting for dark matter particles to strike. The Large Hadron Collider smashes protons together at nearly light speed, searching for dark matter in the debris. Telescopes map dark matter's gravitational effects across galaxy clusters. After decades of searching, we've found precisely nothing. No direct detection, no particle captured, no smoking gun. The absence of detection doesn't mean absence of existence. Dark matter's gravitational effects are undeniable. We see its influence everywhere we look in the cosmos. We just can't see it directly. This invisible scaffolding shapes the universe while remaining completely hidden. What else might be hidden in plain sight? During the Dark Age, dark matter pools into massive halos, some stretching millions of light years across, creating invisible gravitational wells. Where filaments of the cosmic web cross, dark matter accumulates into particularly dense concentrations, and into these dark matter cradles, normal matter falls. Hydrogen and helium gas compress in these invisible valleys. As gas compresses, it heats up, pressure builds. But for millions of years, the heating isn't enough. The temperature rises from 60 Kelvin to hundreds of Kelvin, then thousands, still not enough for fusion. The gas continues to compress, growing denser, hotter, waiting for the threshold. Inside these dark matter halos, normal matter swirls and condenses. Conservation of angular momentum, the same principle that makes ice skaters spin faster when they pull in their arms, causes the gas to rotate faster as it contracts. Turbulence creates eddies and currents in the collapsing cloud. Magnetic fields, though weak, thread through the gas, channeling its flow. We believe this is what happened. Our simulations show it. Our physics predicts it. But we have no direct evidence. No light survived from this epoch. The cosmic dark age earned its name. It's dark to us as well, hidden behind an impenetrable curtain of time and absence. Then, somewhere between 100 and 180 million years after the Big Bang, something changes. The first gas cloud reaches critical conditions. Its core temperature hits 10 million degrees Kelvin. At this threshold, hydrogen nuclei, single protons, move fast enough to overcome their electrical repulsion. They collide, they fuse, releasing energy. The first star ignites, not gradually, not gently. The first stars burst into existence as monsters 200 times our sun's mass. Their surfaces burn at 100,000 degrees Celsius, 10 times hotter than our sun, blazing blue-white with ultraviolet radiation so intense it begins transforming the universe around them. Why so large? Why so different from the sun we orbit today? The answer lies in chemistry, or rather, its absence. The first stars form from pure hydrogen and helium, the only elements the Big Bang created. Modern stars form from gas, enriched with heavier elements, carbon, oxygen, nitrogen, iron, produced by previous stellar generations. These heavy elements act as coolants, radiating energy away, allowing gas clouds to collapse into smaller, cooler stars. But the first stars have no coolants. Their gas remains hot as it collapses. Hot gas resists compression through thermal pressure. Only the most massive clouds, those with hundreds of solar masses, have enough gravity to overcome this pressure and collapse. The result? Stellar behemoths burning with furious intensity. These population 3 stars, so called because they're the third stellar population we theorized, though the first to exist, live fast and die young. 200 solar masses burning at 10 times our sun's temperature exhaust fuel at a prodigious rate. While our sun will burn for 10 billion years, these first stars consume their hydrogen in just 3 million years, a cosmic eye blink. But their brief lives transform everything. Ultraviolet radiation floods outward at the speed of light. This radiation carries enough energy to strip electrons from hydrogen atoms, ionizing the gas. Neutral hydrogen, transparent to most light, becomes ionized hydrogen plasma, which interacts with radiation differently. The process feeds on itself. Ionized regions expand, their boundaries racing outward as radiation reaches new material. The cosmic reionization begins. One star lights up a bubble of ionized gas around itself. Then 10 stars. Then thousands. The bubbles grow, merge, overlap. Within 400 million years, the entire universe transitions from neutral to ionized. Darkness ends. The cosmic dark age gives way to the epoch of reionization. The universe becomes transparent to light for the first time since atoms formed. We can see the evidence today. The cosmic microwave background, that ancient light from when the universe was 380,000 years old, shows a slight polarization pattern caused by reionization. The earliest quasars, supermassive black holes shining when the universe was less than 1 billion years old, show absorption patterns indicating when neutral hydrogen disappeared. The observations match our predictions beautifully, yet mysteries remain. We don't know exactly when the first star formed. Our best estimates range from 100 to 180 million years after the Big Bang, but we have no direct observation to pin it down. We don't know whether stars formed individually or in clusters. We don't know how many first-generation stars existed, or what fraction of them we might still detect today. The James Webb Space Telescope, launched in 2021, is designed to find these first stars. Its infrared vision can penetrate cosmic dust. Its sensitivity can detect faint light from the universe's earliest epochs. Scientists hope to finally image population 3 stars, capturing their unique spectral signatures: pure hydrogen and helium, no heavy elements, burning at extreme temperatures. If we find them, it will answer questions we've pondered for decades, but it will also raise new ones. How did the transition from dark matter halos to luminous stars actually occur? What intermediate stages existed? Did the first stars form in isolation or in groups? How did their radiation affect surrounding gas, enabling or preventing further star formation? When these first giants exhaust their fuel, they don't fade gently. Their cores collapse in less than a second, compressing matter to nuclear density. The collapse releases gravitational energy equivalent to all the light our sun will ever produce in its entire lifetime, released in 1 second. The outer layers rebound from the incompressibly dense core, creating a shockwave that races through the star at 30,000 miles per second. The star explodes as a hypernova, briefly shining with the power of 5 billion suns. But the explosion does more than shine. In the incredible heat and pressure cores reaching hundreds of billions of degrees, nuclear fusion races through the periodic table. Carbon, oxygen, silicon, iron, elements form in seconds that took millions of years to create during the star's life. Even heavier elements, gold, uranium, platinum, form through rapid neutron capture as the shockwave passes through the star's outer layers. These newly forged atoms blast into space at 10% the speed of light, seeding the cosmos with the first heavy elements. The pristine hydrogen and helium universe becomes contaminated, enriched, really with materials that will eventually form planets, atmospheres, and living beings. Every atom heavier than helium in your body was forged in a dying star. The iron in your blood, the calcium in your bones, the oxygen you breathe, all created in stellar furnaces and scattered by explosions. The hypernova leaves behind a black hole. The stellar core, compressed beyond the point of no return, creates a region of space-time so warped that nothing can escape, not even light. These first black holes, 10 to 100 times the sun's mass, become seeds. Over billions of years, some will grow to millions or billions of solar masses, becoming the supermassive black holes we observe at galaxy centers today. But how do stellar mass black holes grow to supermassive ones? The timeline seems too short. A black hole growing by consuming nearby matter should take tens of billions of years to reach millions of solar masses. Yet we observe billion solar mass black holes existing when the universe was less than 1 billion years old. Something allowed rapid growth. Perhaps mergers of many stellar black holes, perhaps direct collapse of massive gas clouds, perhaps processes we haven't yet identified. The Dark Age ends not with a bang, but with countless bangs, stars igniting throughout the universe, their light pushing back the darkness, their deaths enriching space with heavy elements. Within a few 100 million years, the universe transforms from a cold, dark, simple place of hydrogen and helium into a complex, luminous cosmic ecosystem where stars live and die, black holes form and grow, and the building blocks of chemistry spread through space. Yet we've never seen it happen. We've never witnessed a population 3-star, never captured light from the cosmic dark, age directly. Everything we know comes from indirect evidence, computer simulations, theoretical predictions. The universe's hidden age remains largely hidden, its secrets locked behind the absence of surviving light. What we've discovered is only the beginning. Deeper questions remain about how structure emerged from chaos, how the first stars managed to form, how dark matter's invisible hand guided everything we see. The cosmic dark age stands as a reminder that some chapters of history, even cosmic history, may remain forever difficult to read, their evidence faded, their stories told only through the consequences they left behind. And those consequences? They set the stage for everything that follows: the formation of galaxies, the birth of new stellar generations, the creation of planets, and eventually, on at least one world orbiting an unremarkable star, the emergence of beings capable of looking back and asking, how did it all begin? Galaxies emerge, not as random collections, but as organized cities, following invisible blueprints written in dark matter. The first galaxies appear just 400 million years after the Big Bang, small, irregular clumps containing only millions of stars, not the hundreds of billions we see today. These cosmic infants look nothing like the majestic spirals and elegant ellipticals that dominate the modern universe. They're chaotic, turbulent, violent nurseries, where stars form at rates 100 times faster than in our galaxy today. But how do they form at all? The question seems simple until you examine the physics. Gas clouds want to collapse under gravity, yes, but they also want to spin. Conservation of angular momentum means a collapsing cloud spins faster as it shrinks, just as an ice skater spins faster when pulling in their arms. This spin creates centrifugal force that resists further collapse. Left unchecked, the cloud should flatten into a disk and stop contracting. Something must remove angular momentum. Gravitational interactions with dark matter help. Gas losing energy to radiation cooling helps. Turbulent eddies transferring momentum between regions help. But the details, the precise mechanisms that allow gas to lose enough momentum to continue collapsing while retaining enough to form rotating structures, remain poorly understood. We see the results. Galaxies exist. But the step-by-step process from diffuse gas to organized stellar systems still holds mysteries. These cosmic infants collide and merge constantly in the crowded early universe. Space is smaller then, galaxies packed more closely together. When two protogalaxies meet, they don't crash like solid objects. Galaxies are mostly empty space. The distance between stars dwarfs their sizes. Instead, they pass through each other like ghosts, their stars rarely colliding, but their gravity intertwining, pulling them back for another pass, and another, until they merge into a single larger galaxy. The Milky Way itself forms through hundreds of mergers over billions of years. We know this because we can see the evidence today: ghost streams of stars orbiting our galaxy's halo, remnants of smaller galaxies consumed long ago. The Sagittarius dwarf elliptical galaxy is being torn apart by the Milky Way right now, its stars stripping away, joining our galaxy's population. In 4 billion years, the the Andromeda Galaxy will collide with our own, creating a new elliptical galaxy that astronomers have already nicknamed Milkomeda. But deeper questions remain. How do galaxies know what shape to become? Why do some form elegant spirals while others become featureless ellipticals? The traditional answer involves mergers, ellipticals, form from violent collisions that scramble stellar orbits, while spirals grow through gentler accumulation of gas. Yet, we observe spiral galaxies that have undergone major mergers. We see ellipticals in environments where collisions seem unlikely. The relationship between environment, merger history, and final morphology is more complex than we thought. At galactic centers, supermassive black holes grow through a deadly feast. Every large galaxy harbors one of these monsters at its core, a region where gravity has won absolutely, where space-time curves so extremely that nothing, not even light, can escape. The black hole at our galaxy's heart, Sagittarius A star, weighs 4 million suns. We've watched stars orbit this invisible monster at 17,000 miles per second, their elliptical paths tracing the gravity well of something we cannot see but whose presence is undeniable. 4 million solar masses sounds impressive until you learn about Toon 618. This quasar, a supermassive black hole actively consuming matter, weighs 66 billion suns. To put this in perspective, if our Sun were a golf ball, TON 618 would be a sphere larger than Neptune's orbit. It consumes matter equivalent to several hundred Earths every day, shining with the power of 140 trillion suns as infalling matter heats to millions of degrees before crossing the event horizon. How do black holes grow so large? The question has haunted astrophysicists for decades. A stellar mass black hole, 10 to 100 solar masses, formed from a collapsed star, should take tens of billions of years to grow to millions of solar masses by consuming nearby matter. There are physical limits to how fast a black hole can feed. Radiation pressure from the superhot accretion disk pushes away incoming material, creating a natural speed limit called the Eddington limit. Yet we observe billion solar mass black holes existing less than 1 billion years after the Big Bang. They grew too fast. Either black holes can exceed the Eddington limit under conditions we don't understand, or they formed with much larger initial masses than stellar collapse provides, or they grew through rapid mergers with other black holes, or something else entirely happened that we haven't yet conceived. Recent observations deepen the mystery. The James Webb Space Telescope has found black holes that appear overmassive for their host galaxies, black holes weighing more than they should relative to the surrounding stellar population. In the modern universe, a tight relationship exists between black hole mass and galaxy properties. These early black holes violate that relationship. Either they formed before their galaxies fully assembled, or the relationship evolved over cosmic time in ways we didn't predict. These monsters don't just destroy, they regulate galaxy growth through feedback loops. When a black hole feeds actively, becoming a quasar, something remarkable happens. The infalling matter doesn't simply disappear into the black hole. It forms an accretion disk, a swirling vortex of gas orbiting at near light speed, heating through friction to millions of degrees. This superhot disk radiates more energy than entire galaxies of stars, but energy is only part of the story. The black hole launches jets, beams of particles accelerated to 99.9% light speed, shooting out from the poles perpendicular to the accretion disk. These jets, powered by the black hole's spin and magnetic fields through processes we're still working to understand, extend hundreds of thousands of light years into intergalactic space. They plow through gas clouds, heating them, pushing them away from the galaxy. This is black hole feedback. The monster at the galaxy's core heats surrounding gas too much for star formation. Stars require cold, dense gas to form. Heat it to millions of degrees, and it becomes diffuse, unable to collapse. The black hole, by feeding, prevents its own food supply from replenishing. Star formation slows or stops. The galaxy enters a quiescent phase. When the black hole exhausts nearby gas, it goes dormant. The galaxy cools. Gas settles back down. Star formation resumes. Eventually, enough gas accumulates near the center to reawaken the black hole. The cycle repeats. This feedback loop, black hole feeding preventing star formation, starvation allowing it to resume, helps explain why galaxies don't simply convert all their gas into stars. Without it, galaxies would be much brighter, much more star-filled, and would have exhausted their fuel billions of years ago. Yet the details of this feedback remain mysterious. How exactly do jets heat gas? How does radiation pressure push gas entirely out of galaxies? What determines when a black hole switches from dormant to active? Observations show the correlation. Active black holes correlate with reduced star formation, but correlation isn't causation, and the mechanisms remain debated. Spiral arms sweep through galactic disks like cosmic weather patterns. If you could watch a spiral galaxy for 100 million years, time-lapsed into minutes, you'd see something surprising. The spiral arms don't rotate like solid spokes on a wheel. They're density waves, regions of compression moving through the disk at a different speed than the stars themselves. Stars drift into a spiral arm, slow down slightly due to increased gravity, then drift out the other side. The arm persists even as individual stars pass through. This is the density wave theory, proposed in the 1960s to explain a puzzle. Spiral arms should wind up and disappear within a few galactic rotations. The galaxy's center rotates faster than its edges, like a spinning plate. If spiral arms were material structures, they'd twist into ever tighter spirals until they vanished. But galaxies show persistent, well-defined spiral arms billions of years after formation. Density waves solve the problem. They're patterns, not objects, compressions in the stellar disk that persist like traffic jams on a highway. Cars enter the jam, slow down, then exit, but the jam itself remains stationary. Similarly, stars enter spiral arms, enhance them through their gravity, trigger star formation in compressed gas, then exit. The arm remains, fed by continuous stellar traffic, but we don't fully understand what maintains these waves. Computer simulations can create spiral arms, but the arms often look wrong. Too many, too tightly wound, too transient. Some factor is missing from our models. Perhaps it's the influence of dark matter distribution. Perhaps it's magnetic fields threading through the disk. Perhaps it's the complex interplay of stellar feedback, gas dynamics, and self-gravity. The spiral arms exist. We see them in countless galaxies. Yet explaining their exact structure and longevity remains a challenge. Our Sun takes 230 million years to orbit the galaxy's center, a cosmic year. In its lifetime, our Sun has completed only 20 orbits. The galaxy is so vast that even at 500,000 miles per hour, our Sun inches around its orbit at a cosmic crawl. During one of those orbits, about 60 million years ago, our solar system passed through a spiral arm. Did increased radiation from massive young stars in the arm contribute to the extinction event that killed the dinosaurs? The timing is suggestive, but inconclusive. Between the arms lie vast voids where star formation slows, creating quiet neighborhoods in the cosmic city. The interarm regions contain older, redder stars, survivors from previous passages through spiral arms, drifting through the galactic disk's quieter suburbs. These regions see fewer supernovae, less intense radiation, more stable conditions over long periods. Does this matter for life? Perhaps. A planet in a spiral arm faces more radiation, more frequent supernovae, more gravitational perturbations from passing stars. A planet in an interarm region enjoys quieter conditions. Some scientists suggest Earth's position in the Orion spur between two major spiral arms contributes to our biosphere's longevity. Speculation, yes, but suggestive speculation grounded in real differences between galactic environments. The galaxy's disk spans 100,000 light-years, but its dark matter halo extends 600,000 light-years, an invisible suburb dwarfing the visible city. Most of the galaxy's mass exists in this halo, invisible and undetectable except through gravity. The visible galaxy, all those billions of stars, all that gas and dust is just the tip of the iceberg, a luminous core floating in a vast ocean of dark matter. This realization transforms our understanding of galaxies. They're not self-contained islands of stars. They're complex systems where visible matter represents a small fraction of total mass, embedded in massive dark matter structures that extend far beyond the visible edges. The dark matter halo shapes the visible galaxy's rotation, influences its interactions with neighbors, and provides the gravitational well that holds everything together. Within this architecture, stellar populations segregate by age. The galactic bulge and halo contain ancient stars, population 2 stars, formed early in the galaxy's history from gas, slightly enriched by previous stellar generations. These old stars, 10 to 13 billion years old, orbit in random chaotic paths, their motion preserving the memory of the galaxy's violent youth. The disk contains younger stars, population 1 stars like our Sun, formed from gas enriched by many previous stellar generations. These stars orbit in orderly paths around the galactic center, their motion organized by the disk's rotation. The youngest, hottest, brightest stars, O and B-type giants, living only millions of years, concentrate in spiral arms where active star formation occurs. The age gradient tells a story. Galaxies built from the inside out, forming bulges first, then gradually accumulating disk material over billions of years. Or perhaps they formed chaotically, with early mergers creating the bulge while later gentler gas accretion built the gas accretion disk. Or perhaps different galaxies followed different paths. The variety of observed galactic structures suggests multiple formation routes, multiple histories, multiple ways for gravity and gas to collaborate in building cosmic cities. But deeper questions remain. Why do some galaxies keep forming stars for billions of years while others stop? Why do massive ellipticals contain no young stars, while smaller spirals actively birth them? What determines whether a galaxy lives or dies, grows or stagnates? The answers involve black hole feedback, gas supply, merger history, and environmental factors, a complex web of influences that we're still untangling. Galaxy clusters, cities of cities, represent the universe's largest gravitationally bound structures. The Coma cluster contains over 1,000 galaxies in a region 15 million light-years across. Between these galaxies flows intergalactic gas heated to tens of millions of degrees, radiating X-rays, containing more mass than all the galaxy's stars combined, and pervading everything, 5 times more mass than gas and stars together. Dark matter holds the cluster together against the outward pressure of hot gas and the random motions of galaxies. At cluster centers, giant elliptical galaxies, the result of countless mergers, dominate. These galaxies contain trillions of stars but almost no gas, having exhausted their fuel or had it stripped away by interactions with the hot intracluster medium. They're stellar graveyards, home to ancient stars slowly fading, with no new generations to replace them. Why do galaxies in clusters differ from those in isolation? The environment matters. Galaxies in clusters move at millions of miles per hour through hot gas, which strips away their cold gas reservoirs, ram pressure stripping, like a hurricane tearing away a building's roof. Without cold gas, star formation stops. The galaxy reddens as its blue massive stars age and die, leaving only longer-lived red stars. Galaxy harassment, repeated high-speed flybys of neighboring galaxies also transforms cluster members. Each encounter isn't violent enough to merge the galaxies, but disturbs them gravitationally, heating their stellar disks, driving gas toward the center, where the black hole can consume it. Over billions of years and countless encounters, spirals become ellipticals, star-forming galaxies become quiescent, the cluster's population evolves. Yet we're still discovering how clusters themselves form. Current models show dark matter filaments intersecting, creating massive halos where clusters assemble. Galaxies flow down the filaments like beads on cosmic strings, accumulating in the intersection points. The cluster forms hierarchically, small groups merging into larger ones, the process continuing until the present day. The bullet cluster provides evidence for this process. Two galaxy clusters collided 600 million years ago. We see the result today. The galaxies passed through mostly unscathed, too much empty space between stars for collisions. The hot gas collided, slowed, and sits between the clusters. But dark matter, interacting only through gravity, passed through unimpeded. Gravitational lensing shows dark matter concentrated ahead of the gas, separated from it, visual proof that dark matter exists and behaves as theory predicts. This architecture, from individual stars to galaxies to clusters, reveals a universe organized across staggering scales. Patterns repeat: rotation, hierarchy, dark matter dominance, gravity's patient construction. Yet each scale presents unique mysteries. How stars form in molecular clouds, how galaxies shape themselves, how clusters evolve. Each process involves physics we understand, but details that surprise us. What we've discovered is only the beginning. The universe's structure extends beyond what we can see, built on foundations we cannot directly observe, following rules we're still learning. The answer reveals deeper questions. Every observation demands refined theories. The cosmic cities shine brilliantly, but they're built on invisible frameworks we're only beginning to map. And in those gaps between what we observe and what we understand lie the frontiers where discovery awaits. For nearly all human history, the universe consisted of what eyes could see: about 6,000 stars on the clearest night, scattered across the celestial sphere like distant campfires. The moon waxed and waned, planets wandered among fixed stars, comets appeared and vanished. But the fundamental question, how far, how large, what are they, remained beyond reach. The universe was a ceiling painted with lights, close enough to touch if only we could climb high enough. Then, on a January night in 1610, Galileo Galilei points his handmade telescope, a toy, really, magnifying objects just 20 times at Jupiter. He sees 4 points of light near the planet, arranged in a line. The next night, they've moved. The night after, they've moved again. Over weeks of observation, sketched carefully by candlelight, a pattern emerges. These are moons orbiting Jupiter. Not everything orbits Earth. This simple observation shatters a worldview. If moons can orbit Jupiter, perhaps Earth is not the center of all motion. Perhaps Copernicus was right. Earth orbits the Sun, not the reverse. The telescope, barely more powerful than modern binoculars, reveals a truth that naked eyes could never see. We are not at the center. But how far away are these worlds? Parallax should provide the answer, the apparent shift in position when viewed from different locations. Hold your finger at arm's length and alternate closing your eyes. Your finger appears to jump against the background. The closer your finger, the larger the jump. Measure the jump angle and the distance between your eyes, and you can calculate your finger's distance. For centuries, astronomers tried the same with stars, using Earth's orbit as the baseline. As Earth moves around the Sun a distance of 186 million miles from one side to the other, nearby stars should appear to shift against more distant background stars. Yet no shift was detected. Either the stars were unimaginably distant, or Earth didn't move at all. Skeptics of heliocentrism cited the absence of stellar parallax as evidence that Earth remained stationary. 2 centuries pass before Friedrich Wilhelm Bessel finally measures what everyone sought. In 1838, using a precision telescope and months of careful observations, he detects a tiny shift, just 0.314 arc-seconds in the position of the star 61 Cygni. An arc-second is 1/3600th of a degree. Bessel measured a third of that. The precision required staggers the imagination. The distance revealed by this tiny angle, 11 light-years. Light, travelling at 186,000 miles per second, takes 11 years to reach us from 61 Cygni. We see the star as it existed 11 years ago. If it exploded today, we wouldn't know for 11 years. This discovery transforms stars from mysterious lights into distant suns, expanding the universe from thousands of miles to trillions. But deeper mysteries emerge. If stars are distant suns, why do they shine with different colours and brightnesses? Some glow red, others yellow, still others blue-white. Some pulse regularly, others flare unpredictably. In the 1800s, spectroscopy splitting starlight through prisms to reveal the colours it contains shows that different stars contain different elements. More precisely, different stars display the same elements at different temperatures and densities. Annie Jump Cannon, working at Harvard in the early 1900s, classifies 350,000 stars by their spectra. From this massive dataset, a pattern emerges. Stellar spectra fall into discrete categories O, B, A, F, G, K, M, each representing a different surface temperature. O stars burn blue-white at over 30,000 degrees Celsius. M stars glow red at under 3,000 degrees. Our Sun, a G-type star, sits in the middle at 5,500 degrees. This classification reveals something profound. Stars are not random. They follow patterns. They can be categorized, understood, predicted. The universe operates by rules, not caprice. But why do these categories exist? What determines whether a star becomes O or M type? Cecilia Payne, in 1925, provides the answer through her doctoral thesis. Stars differ primarily in temperature, not composition. All stars consist mostly of hydrogen and helium. The temperature determines which spectral lines appear, creating the observed categories. This discovery that the universe is mostly hydrogen seems almost disappointing in its simplicity. Yet it raises new questions. Why hydrogen? Why these proportions? Where did elements heavier than helium come from? In 1923, Edwin Hubble photographs the Andromeda Nebula using the 100-inch telescope at Mount Wilson. Andromeda appears as a fuzzy spiral in the night sky, long assumed to be a gas cloud within our galaxy. But Hubble identifies a Cepheid variable star within Andromeda, a type of star whose pulsation period relates directly to its intrinsic brightness. Measure the period, calculate the true brightness, compare it to observed brightness, and you can determine distance. The calculation reveals Andromeda lies 2 million light-years away, far beyond the Milky Way's known boundaries. The nebula is actually another galaxy, an island universe containing hundreds of billions of stars, separated from our own galaxy by vast intergalactic voids. The universe contains not one galaxy but billions. The scale of creation expands beyond anything previously imagined. Then comes Hubble's second bombshell. In 1929, comparing distances to galaxies with their spectral shifts, he discovers that galaxies race away from us. More distant galaxies flee faster. The relationship is linear. Double the distance, double the recession speed. This is Hubble's law, evidence that space itself expands, carrying galaxies along like raisins in rising bread dough. If galaxies fly apart today, running the clock backward means they were closer together yesterday, touching in the distant past, compressed into a singular point at the beginning. The universe had a beginning. Time had a start. Before Hubble, most scientists imagined an eternal, unchanging cosmos. After Hubble, that comfortable assumption collapses. The universe was born, but deeper questions remained. Born from what? Born how? What existed before? These questions, unanswerable in 1929, would haunt cosmology for decades. The accidental discovery that changes everything comes in 1964. Arno Penzias and Robert Wilson, engineers at Bell Labs, try commissioning a sensitive radio antenna for satellite communications, but they cannot eliminate a persistent hiss from every direction in the sky. They check for equipment problems. They find none. They consider terrestrial sources. They find none. They even clear pigeon droppings from the antenna, wondering if bird waste somehow generates radio noise. The hiss remains. Meanwhile, just 30 miles away, physicists at Princeton University predict that if the Big Bang happened, radiation from the hot early universe should still permeate space, cooled by expansion to just a few degrees above absolute zero, detectable as microwave frequency radio waves. Penzias and Wilson's unexplained hiss matches the prediction perfectly. They'd discovered the cosmic microwave background, the cooled remnant of the Big Bang itself, light that has travelled for 13.8 billion years, reaching us from every direction simultaneously. This discovery transforms cosmology from speculation to science. The Big Bang is not just theory but observable fact. The universe was once incredibly hot and dense. It expanded and cooled. The evidence surrounds us, a faint glow of ancient light filling all of space. Every cubic centimetre of empty space contains about 400 microwave photons, left over from the Big Bang fossils of creation, older than stars, older than galaxies, witnesses to the universe's birth. But the cosmic microwave background reveals more than just the Big Bang's occurrence. Its temperature varies by 1 part in 100,000 across the sky, tiny ripples representing density variations in the early universe. Regions slightly denser than average appear slightly warmer. Regions slightly less dense appear slightly cooler. These variations, imprinted when the universe was 380,000 years old, are the seeds from which all structure grew. Slightly denser regions attracted more matter through gravity, growing denser still, eventually forming galaxies and galaxy clusters. Every galaxy in the universe traces its lineage to these quantum fluctuations, magnified by cosmic inflation. The Hubble Space Telescope, launched in 1990, revolutionizes astronomy by observing from above Earth's distorting atmosphere. In 1995, astronomers point Hubble at a patch of sky in Ursa Major that appears completely empty. No visible stars, no nebulae, nothing but darkness. The patch is tiny, smaller than a grain of sand held at arm's length. They expose the telescope's cameras for 10 days, collecting every photon arriving from that direction. The resulting image, called the Hubble Deep Field, stuns everyone. That empty patch contains 3,000 galaxies, not 3,000 stars, 3,000 galaxies, each containing billions of stars. Some appear as elegant spirals, others show irregular, chaotic structures. Some are clearly interacting, their gravity pulling at each other, and they exist at different distances, some relatively close, others so distant their light has travelled for over 12 billion years to reach us. If 3,000 galaxies exist in such a tiny patch of sky, how many exist in total? The calculation suggests roughly 400 billion galaxies in the observable universe. Multiply by hundreds of billions of stars per galaxy, and the universe contains more stars than grains of sand on all Earth's beaches. The numbers exceed comprehension, yet even this understates reality. The Hubble Deep Field images only the observable universe, the region from which light has had time to reach us since the Big Bang. Beyond the observable horizon, the universe likely extends infinitely, containing infinite galaxies, infinite stars, infinite worlds. We can never observe these regions because their light hasn't reached us yet and, due to accelerating expansion, never will. The universe is larger than we can ever know. In 2003, the Wilkinson Microwave Anisotropy Probe maps the cosmic microwave background with unprecedented precision, measuring its temperature variations to millionths of a degree. The data reveals the universe's composition: 4.9% normal matter, 26.8% dark matter, 68.3% dark energy. Everything we see, all stars, planets, gas, dust, everything made of atoms, comprises less than 5% of the universe's contents. The rest is invisible, mysterious, known only through indirect effects. The data also reveals the universe's age, 13.8 billion years, with an uncertainty of less than 1%. The Planck satellite, launched in 2009, refines this further, measuring 13.799 billion years. We know the universe's age more precisely than we know the age of most rocks on Earth, but deeper questions remain. Why does the universe have the composition it does? Why 5% matter, 27% dark matter, 68% dark energy? Change these ratios even slightly, and the universe would look completely different. Too much dark energy and galaxies never form. Too much dark matter and everything collapses into black holes. Too much normal matter and stars burn out too quickly for life to evolve. The cosmic microwave background shows the universe at age 380,000 years, the moment when atoms formed and light broke free. But what happened before that moment? The universe was opaque then, light unable to travel far before scattering off free electrons. We cannot see past this cosmic curtain. The first 380,000 years, the era when matter and antimatter annihilated, when nuclei formed, when physics operated at energies we can barely simulate in particle, accelerators remains hidden behind an impenetrable barrier. Or does it? Gravitational waves, ripples in spacetime itself, could potentially carry information from before the cosmic microwave background era. They travel through matter without scattering, unimpeded by the early universe's opacity. If we could detect primordial gravitational waves from the Big Bang itself, we might glimpse conditions at impossibly early times, perhaps even the inflationary epoch. In 2014, astronomers announced detection of primordial gravitational waves in the cosmic microwave background's polarization pattern. The discovery, if confirmed, would provide direct evidence for cosmic inflation. But further analysis reveals the signal came from dust in our own galaxy, not from the early universe. The true signal, if it exists, remains undetected. The universe guards its earliest secrets carefully. The James Webb Space Telescope, launched in 2021 and positioned 1 million miles from Earth, begins operations in 2022. Its infrared vision allows it to see through cosmic dust and detect the universe's first galaxies, those forming just a few 100 million years after the Big Bang. Early results astound astronomers. Galaxies appear more mature, more structured, more massive than expected at such early times. Either galaxies formed faster than models predict, or our understanding of early cosmic evolution requires revision. Each expansion of observational capability reveals surprises. Each new instrument detects phenomena theorists didn't predict. The universe is stranger than we imagine, perhaps stranger than we can imagine. What we've discovered, that the universe began, that it expands, that it contains hundreds of billions of galaxies, required centuries of careful observation and brilliant insight. What remains unknown might dwarf what we've learned. We've mapped less than 1% of the universe's volume in detail. We've identified less than 1% of all galaxies individually. We've studied perhaps 1/1,000,000th of all star systems closely. The cosmic census has barely begun. In the unexplored vastness, what wonders await discovery? What new phenomena, what unexpected structures, What violations of our carefully constructed models? The Great Awakening continues. Each generation sees farther, measures more precisely, understands more deeply. Yet each generation also discovers how much remains unknown. The universe reveals itself slowly, grudgingly, always keeping some mysteries hidden just beyond our current reach. And perhaps that's the greatest discovery of all, that the universe is knowable but never fully known, understandable but never completely understood, a puzzle with infinite pieces that rewards every effort to solve it, with glimpses of ever deeper mysteries. Until 1992, humanity knew 9 planets all orbiting our Sunday: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto comprised the complete catalogue of worlds. We assumed planets were common, yes, but we had no proof. No planet had ever been detected beyond our solar system. For all we knew, planetary systems might be rare accidents of stellar formation, cosmic flukes that occurred only under special circumstances. Then astronomers Alexander Wolfsjan and Dale Frail detect a wobble in a pulsar's spin. Pulsars, rapidly rotating neutron stars, emit radio beams like cosmic lighthouses, their pulses arriving with clock-like precision. But PSR B 1257 plus 12 shows timing irregularities, slight variations in when pulses arrive. The pattern repeats regularly, suggesting orbiting masses tugging the pulsar back and forth through their gravitational influence. The interpretation staggers belief. Planets orbiting a pulsar, not just one planet but 3, with masses comparable to Earth. These worlds orbit a stellar corpse, the collapsed remnant of a supernova explosion, bathed in deadly radiation, subjected to intense magnetic fields. How did they survive the supernova that created their sun? Did they form afterward from the debris disk? Are they the dense cores of gas giants whose atmospheres were stripped away by the explosion? We still don't know. Pulsar planets remain mysterious. Rare objects, only a handful, have been confirmed in 3 decades of searching. But their discovery proves planets exist beyond our solar system. The question shifts from, do other planets exist, to how many exist? The first planet around a normal Sun-like star, 51 Pegasi b, discovered in October 1995 by Michel Mayor and Didier Queloz, shocks everyone. Not because planets exist around other stars, but because this planet violates everything we thought we knew about planetary systems. It's a gas giant, roughly half Jupiter's mass, orbiting closer to its star than Mercury orbits our Sunday. Its orbital period, 4.2 days. Its surface temperature, 1,000 degrees Celsius. This hot Jupiter shouldn't exist. Gas giants, according to all formation models, should form beyond the frost line, the distance from a star where temperatures drop low enough for water and other volatiles to freeze. In our solar system, Jupiter and Saturn formed far from the Sun where ice could accumulate, building massive cores that captured enormous hydrogen and helium atmospheres. Close to the star, heat prevents ice formation, limiting planet growth to rocky worlds. So how did 51 Pegasi b arrive at such a close orbit? It must have formed farther out and migrated inward. But what drives planetary migration? Gravitational interactions with the protoplanetary disk might pull young planets toward their stars. Scattering events, close encounters with other planets, might throw some onto wild orbits that eventually circularize close to the star. Tidal interactions with the disk might gradually modify orbits over millions of years. Each mechanism produces different outcomes, different orbital characteristics, different final configurations. By studying hot Jupiter populations, their frequencies, orbital properties, host star characteristics, we can test these theories. But 3 decades after the first discovery, the relative importance of different migration mechanisms remains debated. We know hot Jupiters migrated. We don't know precisely how. The Kepler Space Telescope launches in 2009 and transforms everything. Rather than detecting planets through stellar wobbles, the radial velocity method that found 51 Pegasi b Kepler watches for transits. When a planet crosses in front of its star from our perspective, it blocks a tiny fraction of starlight. For an Earth-sized planet crossing a Sun-like star, the dimming amounts to just 0.01%, detecting a firefly crossing a searchlight from 1,000 miles away. Kepler monitors 150,000 stars simultaneously, taking measurements every 30 minutes for years. The data stream reveals thousands of transit signals dips in, brightness repeating with precise periods. Some transits show large planets blocking several percent of starlight. Others show Earth-sized worlds causing barely detectable dimming. Some planets orbit in days, others in years. The diversity astounds astronomers. In 9 years of operation, Kepler discovers 2,700 confirmed planets and identifies thousands more candidates awaiting confirmation. The mission reveals that planets outnumber stars on average. Every star hosts at least one planet. Multiply by hundreds of billions of stars per galaxy, by hundreds of billions of galaxies, and the universe contains more planets than we can count, more worlds than we can visit, more potential homes for life than we can search. But the variety defies imagination. HATP 7b, a gas giant tidally locked to its star, experiences temperatures of 2,700 degrees Celsius on its day side. High-altitude winds on this scorched world carry clouds of corundum aluminum oxide crystals, the mineral that forms rubies and sapphires. It literally rains liquid ruby and sapphire on this alien world, gemstones condensing from vapor in the cooler upper atmosphere and falling as molten drops. HD 18973-3b, a deep blue planet similar in size to Neptune, endures winds of 5,000 miles per hour. These supersonic gales carry silicate particles, glass shards sideways through the atmosphere. The planet's color comes from atmospheric molecules scattering blue light, similar to Earth's sky. But where Earth's winds carry water droplets, HD 18973-3b's, tempests hurl molten glass at speeds that would cross the United States in 30 minutes. Kepler 16b orbits 2 suns simultaneously, a circumbinary planet like Luke Skywalker's fictional Tatooine. Standing on its surface, if it had a solid surface, which it doesn't, being a gas giant, you would see 2 suns setting, one yellow and one red. Their combined light creating double shadows. The planet's orbit remains stable despite complex gravitational interactions with both stars. But how did it form in such a dynamically chaotic environment? Protoplanetary disks around binary stars should be unstable, their material ejected or consumed before planets can form. Yet circumbinary planets exist, dozens confirmed, their presence challenging formation theories. The search for Earth's twin intensifies with each discovery. Astronomers identify the habitable zone, the orbital range where liquid water could exist on a planet's surface, neither boiling away nor freezing solid. Too close to the star, water evaporates. Too far, it freezes. But in the Goldilocks zone, conditions might be just right for life as we know it. Kepler 452b orbits a sun-like star in the habitable zone. The planet is 60% larger than Earth, though at 1.5 times Earth's diameter, gravity would make a 100-pound person weigh 150 pounds. Its year lasts 385 days, nearly identical to Earth's. Its sun, slightly larger and older than ours, provides similar illumination. If Kepler 452b has an atmosphere, and we don't know whether it does, temperatures might allow liquid water. But deeper questions remain. Does size matter? Earth-sized planets seem like better candidates for life, but Neptune-sized worlds might host habitable moons. Jupiter's moon Europa harbors an ocean beneath its icy crust. Saturn's moon Enceladus shows geysers erupting from subsurface seas. If moons in our solar system contain more liquid water than Earth, perhaps gas giants in other systems' habitable zones could host moon worlds teeming with life. Proxima Centauri b offers our nearest potentially habitable world, orbiting just 4.2 light-years away, near enough that advanced propulsion systems might reach it within a human lifetime. The planet orbits in the habitable zone of Proxima Centauri, a red dwarf star much cooler and dimmer than our Sunday. To receive equivalent warmth, Proxima b orbits 25 times closer to its star than Earth does to the Sun, completing an orbit every 11 days. But proximity creates problems. Red dwarf stars unleash powerful stellar flares, magnetic eruptions that release as much energy in minutes as the star normally emits in days. These flares bathe nearby planets in intense radiation and charged particles, potentially stripping away atmospheres, sterilizing surfaces, making life impossible. Does Proxima b have a magnetic field strong enough to deflect stellar wind? Does it have an atmosphere thick enough to absorb radiation? We don't know. TRAPPIST-1 astounds everyone in 2017 with 7 Earth-sized planets, 3 in the habitable zone, orbiting an ultra-cool dwarf star 40 light-years away. The planets orbit so closely that standing on one world, neighboring planets would appear larger than our moon, close enough to see weather patterns, polar caps, perhaps even city lights if civilizations exist there. The entire system fits within the orbit of Mercury. If transported to our solar system, all 7 planets would fit between the Sun and Mercury's orbit. The tightly packed configuration creates complex gravitational interactions. Each planet tugs on its neighbors, causing orbital resonances the planet's periods relate through simple ratios like 3:2 or 4:3. These resonances stabilize the system, preventing planets from spiraling into the star or flying off into space. But they also mean the planets formed where we find them, never migrating significantly. This challenges migration theories that require planets to move from formation sites to final orbits. The James Webb Space Telescope begins analyzing exoplanet atmospheres in 2022, splitting starlight passing through planetary atmospheres during transits into component wavelengths. Different molecules absorb specific wavelengths, creating spectral fingerprints. Water vapor absorbs infrared light at particular wavelengths. Methane has its own signature, carbon dioxide another. By measuring which wavelengths are absorbed during transits, we can determine atmospheric composition. Early results detect water vapor, methane, and carbon dioxide in several exoplanet atmospheres. But the atmospheres don't quite match predictions. Some planets show more clouds than expected, obscuring spectral features. Others display unexpected molecular combinations, suggesting chemistry we don't fully understand. Every planet seems unique, defying attempts at simple categorization. The search for biosignatures, chemical signs of life, focuses on molecular combinations that seem unlikely without biological processes. Oxygen plus methane in the same atmosphere seems promising, since these gases react chemically and should quickly disappear unless constantly replenished. On Earth, photosynthesis produces oxygen while bacteria and other organisms produce methane. Finding both together on an exoplanet might suggest similar biological processes. But nature is tricky. Abiotic processes, geological activity, photochemistry, volcanic outgassing can also produce oxygen and methane under certain conditions. A single detection wouldn't prove life exists. We'd need multiple biosignatures, multiple lines of evidence, careful analysis ruling out non-biological explanations, and even then, we'd have uncertainty, probability, not proof. What if life uses different chemistry than Earth life? What if alien biospheres produce molecules we wouldn't recognize as biosignatures? Silicon-based life, if it exists, might have completely different metabolic byproducts, Life in liquid methane oceans on tangent-like worlds might operate through chemistry we've never imagined. We search for life as we know it because we don't know what else to search for, but the universe might contain forms of life utterly alien to our experience. Rogue planets, worlds drifting through space without stars, might outnumber starbound planets. Gravitational scattering during planetary system formation can eject planets entirely, sending them on lonely journeys through the galaxy. Surveys suggest the galaxy contains billions of rogue planets, wandering in darkness, heated only by residual formation energy and radioactive decay. Could life exist on such worlds? Unlikely on the surface, frozen in eternal night. But deep underground, geothermal energy might warm subsurface oceans. On Earth, life thrives in deep caves, in ocean trenches, in rock fractures miles below the surface, environments that never see sunlight, powered by Earth's internal heat. Similar life might persist on rogue planets, undetectable, unknowable, persisting billions of years in darkness. Ocean worlds appear common: Europa, Enceladus, Titan, Ganymede, Callisto. 5 moons in our solar system likely harbour subsurface oceans, containing more liquid water combined than Earth's surface oceans. If our solar system, with just 1 star and 8 planets, has 5 ocean worlds, how many might exist across the galaxy? Billions? Trillions? These hidden oceans, locked beneath ice shells kilometers thick, might be the most common habitats for life in the universe. We can detect them through gravitational measurements, surface features suggesting subsurface liquid, and analysis of erupting geysers. But exploring them requires missions that can drill through ice, deploy submarines into alien seas, search for life in environments that never see sunlight. Such missions lie decades in the future, tantalizing possibilities that showcase how much remains unexplored even in our own cosmic neighborhood. Planet formation itself remains mysterious, despite decades of study. We understand the basic process. Dust grains in protoplanetary disks stick through static electricity, growing from microns to millimeters to meters. Meter-sized objects collide and merge, building kilometer-sized planetesimals. Planetesimals accumulate through gravity, forming planet embryos. Embryos collide in a final stage of violent impacts, producing planets, but details elude us. How do meter-sized objects survive to become planetesimals? At this size, they experience maximum drag from surrounding gas, causing them to spiral into the star within a few hundred years. Something must accelerate growth past this hazard zone, but what? Turbulence might concentrate particles into dense clumps that collapse directly to planetesimals. Streaming instabilities might allow small rocks to collectively trigger gravitational collapse, or perhaps electromagnetic effects create locally stable regions where growth can proceed. Each theory explains some observations while struggling with others. No single model accounts for the full diversity of observed planetary systems: hot Jupiters, super-Earths, compact multi-planet systems, widely separated giants, circumbinary planets, rogue worlds. Planet formation appears to be less a single process than a collection of related processes, each operating under different conditions, producing different outcomes. Super-Earth's planets, larger than Earth but smaller than Neptune, represent the most common planet type in the galaxy. Our solar system contains none, making them mysterious despite their abundance. Are they rocky worlds scaled up from Earth? Are they mini-Neptunes with thick hydrogen atmospheres? The transition from rocky to gaseous probably occurs somewhere between 1 and 2 Earth radii, but we don't know exactly where. Some super-Earths orbit so close to their stars that their surfaces are molten lava. Others reside in habitable zones where conditions might permit liquid water. Without visiting these worlds directly or analyzing their atmospheres in detail, we can only speculate about their nature. They might be covered in deep oceans, their entire surfaces underwater. They might have thick atmospheres creating crushing surface pressures. They might be completely unlike any world we've imagined. The planet revolution continues. TESS, the Transiting Exoplanet Survey satellite, launched in 2018, scans the entire sky for transiting planets around bright nearby stars. Ground-based surveys like M-Earth and Speculus search for planets around the smallest, coolest stars. Future missions like Plato and Ariel will characterize thousands more worlds, analyzing their atmospheres, measuring their masses, determining their compositions. But we've explored just the nearest cosmic suburbs. The Kepler field covered 0.25% of the sky. TESS covers more area but focuses on the brightest stars, missing fainter ones that comprise the majority. Most planets in the galaxy remain undiscovered, most star systems unexplored, most worlds unknown. And even among discovered planets, how many harbor life? We've found thousands of worlds, but we haven't detected life on any. This absence might mean life is rare, or it might mean our detection methods aren't sensitive enough yet. Or perhaps life is common, but intelligent life is rare. Or perhaps intelligent life is common, but technological civilization is brief, burning out before making contact. The Fermi paradox looms. If life is common, where is everyone? What we've discovered is extraordinary. Planets are everywhere, worlds beyond count, more planetary diversity than anyone predicted. What remains unknown might be even more remarkable. Whether any of those trillions of worlds harbor life, whether we'll ever detect it, whether the universe contains other beings looking up at their own stars, wondering if they're alone, asking the same questions we ask, discovering they're part of a cosmos filled with worlds waiting to be explored. In 1933, Swiss astronomer Fritz Zwicky studies the Coma Cluster, a collection of over 1,000 galaxies, 290 million light-years away. He measures how fast galaxies move within the cluster, expecting their velocities to match the cluster's visible mass. More massive clusters should hold galaxies more tightly through gravity, limiting their speeds. Less massive clusters should allow faster movement. The numbers don't match. Galaxies move far too fast. At their observed speeds, thousands of miles per second, they should have escaped the cluster billions of years ago, flying off into intergalactic space like sparks from a dying fire. Yet they haven't. The cluster remains bound, stable, its galaxies held together by something invisible. Zwicky calculates that visible matter, all the stars in all the galaxies, accounts for only about 1/6 of the mass needed to explain the observed velocities. Something else, something that doesn't shine, must provide the extra gravity. He calls it dunkle materie, dark matter. The term sounds mysterious, almost mystical, but it's simply descriptive. Matter that is dark, that doesn't emit light, that reveals itself only through gravity. The scientific community largely ignores Zwicky's findings. The idea seems too radical, too speculative. Perhaps his velocity measurements are wrong. Perhaps galaxy masses are underestimated. Perhaps Newtonian gravity breaks down at cluster scales. Explanations that preserve conventional understanding seem preferable to invoking invisible matter. 4 decades pass before Vera Rubin provides compelling evidence that Zwicky was right. In the 1970s, Rubin measures rotation curves of spiral galaxies, how fast stars orbit at different distances from galactic centers. Newtonian mechanics makes clear predictions. Stars farther from the center should orbit slower, just as outer planets in our solar system orbit slower than inner ones. Mercury races around the Sun in 88 days. Neptune takes 165 years. The relationship between distance and orbital speed follows precise mathematical laws, but galaxies don't follow these laws. Stars at galaxy edges orbit just as fast as stars near the center. Plot orbital velocity versus distance, and instead of declining with distance as expected, the curve stays flat, constant velocity regardless of radius. This flat rotation curve violates everything Newton taught us about gravity and orbital mechanics, unless invisible matter surrounds galaxies. If dark matter forms massive halos extending far beyond visible stars, halos containing 5 times more mass than all the stars, gas, and dust combined, then the rotation curves make sense. The extra mass provides extra gravity, holding outer stars in fast orbits despite their great distance from the galactic center. Rubin studies galaxy after galaxy. Every spiral shows the same pattern. Flat rotation curves implying dark matter halos appear universal. This is not a measurement error or an anomaly affecting 1 or 2 galaxies. It's a fundamental feature of galactic structure. Something invisible outweighs everything we can see 5 to 1. What is this dark matter? Scientists propose candidates. WIMPs, weakly interacting massive particles, represent a leading theory. These hypothetical particles would interact through gravity and possibly the weak nuclear force, but not electromagnetism, explaining why they don't emit, absorb, or reflect light. They'd pass through ordinary matter almost unimpeded, billions flowing through your body every second without leaving any trace. Axions offer another possibility: extraordinarily light particles, perhaps 1 trillion times lighter than electrons, created in the early universe. Sterile neutrinos, heavier cousins of known neutrinos, might account for some dark matter. Primordial black holes, formed in the first second after the Big Bang, when quantum fluctuations created density variations large enough to collapse directly, could contribute to dark matter's total mass. Scientists hunt dark matter in abandoned mines, miles underground, where cosmic radiation can't interfere. Detectors sit in chambers carved from solid rock, shielded by millions of tons of earth, waiting for the rare collision between a dark matter particle and a detector atom. The collision would deposit a tiny amount of energy, enough to detect if your equipment is sensitive enough, if the background noise is low enough, if you wait long enough. The Large Hadron Collider smashes protons together at 99.9999% light speed, recreating conditions similar to the early universe when dark matter particles might have been produced. Scientists search through collision debris for missing energy and momentum signs that dark matter particles were created but escaped detection, their presence revealed only by what's absent. Telescopes map dark matter's distribution using gravitational lensing. Massive objects bend space-time, curving the path of light passing near them. When light from a distant galaxy passes through a dark matter halo, its path bends, creating distorted, magnified images. By measuring these distortions across the sky, astronomers map dark matter's distribution, even though they can't see it directly. After decades of searching, we've found precisely nothing. No direct detection of dark matter particles, no WIMPs captured in underground detectors, no axions identified in collision debris, not a single dark matter particle held in our hands, examined in our laboratories, confirmed through direct measurement. Yet the evidence for dark matter's existence is overwhelming. Galaxy rotation curves require it. Cluster dynamics demand it. The cosmic microwave background's temperature variations imply it. Computer simulations of cosmic structure formation need it to match observations. Gravitational lensing maps its distribution across the universe. The Bullet cluster provides perhaps the most striking evidence. 2. Galaxy clusters collided 600 million years ago at speeds of millions of miles per hour. When the collision occurred, the hot gas in each cluster plasma, heated to tens of millions of degrees, slammed together and stopped, held back by electromagnetic interactions and gas pressure. The gas is now visible between the clusters as an X-ray emitting cloud, marking the collision site. But dark matter, interacting only through gravity, passed through unimpeded. Gravitational lensing reveals where the mass actually is, not in the hot gas cloud between the clusters, but ahead of it, concentrated where the galaxies themselves are. The collision separated normal matter from dark matter, providing visual proof that dark matter exists as something distinct from ordinary matter. We see the effect clearly. Dark matter and visible matter occupy different locations, separated by the collision. If dark matter didn't exist, if galaxy rotation curves and cluster dynamics had some other explanation involving modified gravity, this separation couldn't occur. Gravity doesn't separate from itself. The bullet cluster shows unambiguously that dark matter is real, is separate from normal matter, and behaves as theory predicts. So what is it? We've eliminated many candidates. It's not brown dwarfs, failed stars too small to ignite fusion. We've surveyed the sky and haven't found enough to account for dark matter's mass. It's not black holes, at least not stellar mass black holes formed from collapsed stars. Their formation creates elements that we detect in old stars but don't. It's not gas or dust, we can detect those through their thermal emission or absorption of light. Dark matter must be something else. Some new particle, some exotic form of matter, some phenomenon beyond the standard model of particle physics. The standard model, our best theory of particles and forces, describes everything we've ever detected in laboratories, every particle predicted by the FRE5. Standard model has been found. Every force behaves as equations predict. The theory works brilliantly, except it doesn't account for dark matter. The standard model contains no particles with dark matter's properties, massive enough to provide significant gravity, stable enough to survive since the Big Bang, non-interacting enough to remain invisible. Dark matter's existence proves the standard model is incomplete. Physics requires new particles, new forces, perhaps entirely new principles we haven't yet imagined. Then comes an even greater mystery. In 1998, two teams of astronomers studied distant supernovae, massive stellar explosions so consistent in brightness that they serve as cosmic lighthouses. Type Ia supernovae occur when white dwarfs accumulate too much mass and explode, releasing energy equivalent to 5 billion suns shining for weeks. Because the trigger mass is always the same, the explosions always release similar energy, making them extraordinarily useful as distance indicators. Both teams expect to measure the universe's deceleration from gravity. After the Big Bang, the universe began expanding, but gravity pulls everything together, slowing expansion like a ball thrown upwards, slowing in Earth's gravity. The question isn't whether expansion slows, but how much, whether gravity is strong enough to eventually stop and reverse expansion, causing the universe to collapse in a big crunch, or whether expansion continues forever but gradually slows. The teams measure distant supernovae, determine their distances, compare to their redshifts how much their light has stretched due to cosmic expansion. The relationship between distance and redshift reveals expansion history. If expansion is slowing, distant supernovae should appear brighter than expected, because they're closer than they'd be in a non-decelerating universe. The supernovae appear dimmer, not brighter. Dimmer. They're farther away than expected. The universe isn't decelerating, it's accelerating. Expansion speeds up over time, driven by something that works opposite to gravity, something that pushes space apart rather than pulling it together. The discovery shocks everyone. Nothing in known physics suggests the universe should accelerate. Gravity attracts. It pulls things together. There's no repulsive force in general relativity strong enough to drive cosmic acceleration. Yet the data is clear. Multiple independent teams confirm it. The universe expands faster today than it did 1 billion years ago, faster than it did 2 billion years ago. Something makes expansion accelerate. Scientists call this something dark energy, though the name explains nothing. We don't know what it is. We don't know where it comes from. We don't know why it exists. Dark energy is simply the name we give to whatever causes accelerating expansion, a placeholder for ignorance, a label marking a mystery we haven't solved. Dark energy comprises 68% of the universe's total energy. Dark matter represents 26%. Normal matter atoms, molecules, everything we can see and touch accounts for less than 5%. The universe is mostly dark energy. We don't know what it is. Every cubic meter of empty space contains dark energy equivalent to 3 hydrogen atoms. That doesn't sound like much. 3 atoms per cubic meter is essentially vacuum. But space is vast. Integrate over cosmic volumes, and dark energy dominates everything else. More remarkably, dark energy's density doesn't dilute as space expands. When space doubles in volume, dark energy's total amount doubles too, maintaining constant density. This is bizarre. Normal matter dilutes with expansion, double the volume, and matter spreads out, becoming half as dense. Dark matter behaves the same way, but dark energy doesn't. It's a property of space itself, not something in space. Create more space through expansion. You create more dark energy. The universe generates dark energy from nothing, continuously, forever. What could cause this? Quantum mechanics suggests empty space isn't truly empty. Virtual particle pairs constantly pop into existence for brief instants before annihilating quantum fluctuations that create a vacuum energy permeating all space. Perhaps vacuum energy is dark energy, but the numbers don't work. Calculate vacuum energy from quantum field theory, and you get a value 120 orders of magnitude larger than observed dark energy. That's not a small discrepancy. It's the worst prediction in physics history, off by a factor of 10 to the 120th power. If vacuum energy were this large, the universe would have accelerated so violently that atoms could never form. We wouldn't exist to ask the question. Something cancels vacuum energy to extraordinary precision, leaving only the tiny residual we observe as dark energy. What performs this cancellation? We have no idea. Some unknown symmetry, some fine-tuning of fundamental constants, some principle we haven't discovered. The cosmological constant problem, why dark energy has the value it does, remains one of physics' deepest puzzles. Einstein predicted something like this. In 1917, trying to find solutions to his general relativity equations that described a static universe, the prevailing cosmological assumption, then he added a term called the cosmological constant. This constant represented a uniform energy density permeating space, providing repulsive pressure that exactly balanced gravity's attractive force, allowing the universe to remain static. When Hubble discovered cosmic expansion in 1929, Einstein allegedly called the cosmological constant his greatest blunder. If he'd trusted his equations without adding the constant, he would have predicted expansion before Hubble observed it, potentially the greatest prediction in physics history. Instead, he modified his equations to match the prevailing but incorrect assumption of a static universe. Now we know Einstein was right all along, though for reasons he didn't anticipate. The cosmological constant exists. It causes accelerating expansion. Dark energy is real. Einstein's blunder turns out to be one of his greatest insights. Yet we still don't understand why dark energy has precisely the value it does. The value is neither zero, which would be natural, nor enormous, which quantum mechanics predicts. It's finely tuned to a value that allowed structure formation before acceleration dominated. Earlier, and galaxies never form. Later, and we might not yet observe acceleration. The value seems suspiciously convenient for our existence. Some scientists invoke the anthropic principle. We observe dark energy with this value because we couldn't exist to make observations if it had a different value. In a universe with excessive dark energy, structure never forms and life never arises. In a universe with zero dark energy, perhaps some other fine-tuning prevents life. We find ourselves in a universe with this particular dark energy value because it's necessary for observers to exist. But this explanation leaves many unsatisfied. It doesn't explain why the value is what it is, only why we observe it. The mystery remains: what is dark energy? Why does it exist? And why does it have this particular value? Alternative explanations exist. Perhaps dark energy isn't constant but changes over time. Quintessence, a dynamic field that evolves as the universe ages. Perhaps general relativity breaks down at cosmic scales and needs modification, explaining acceleration without invoking dark energy. Perhaps we're misinterpreting observations. Some unknown systematic effect makes distant supernovae appear dimmer than they are. Yet every new measurement confirms acceleration. Cosmic microwave background observations, baryon acoustic oscillations, gravitational lensing statistics, galaxy cluster, counts multiple independent methods all point to dark energy with consistent properties. If it's an error, it's an incredibly consistent error, affecting completely different measurements in exactly the same way. The universe's far future depends on dark energy's nature. If dark energy remains constant, acceleration continues forever. Galaxy clusters beyond our local group will eventually accelerate away faster than light, disappearing beyond the cosmic horizon. In 100 billion years, future astronomers will see only a merged Milky Way Andromeda galaxy surrounded by darkness, with no evidence other galaxies ever existed. If dark energy strengthens over time, phantom energy acceleration could intensify until it overwhelms all forces. In tens of billions of years, galaxies would be torn apart, then solar systems, then planets, then atoms themselves in a big rip, space-time shredding into infinite expansion. If dark energy weakens, acceleration might slow or even reverse. Gravity could regain control, pulling everything back together in a big crunch, possibly bouncing into a new Big Bang. The universe might be cyclic, expanding and contracting eternally, each cycle potentially different, each Big Bang creating a universe with unique properties. We don't know which future awaits. The universe's fate depends on dark energy's properties, which we don't understand. We can measure dark energy's current effects, but we can't predict its future behavior because we don't know what it is. In 2015, the Laser Interferometer Gravitational Wave Observatory detects gravitational waves for the first time. Ripples in space-time itself caused by two black holes spiraling together and merging. This detection opens an entirely new way to study the universe. Gravitational waves travel through matter unimpeded, carrying information about some of the universe's most violent events. Gravitational wave astronomy might help solve dark energy's mystery by measuring how gravitational waves travel across cosmic distances. We can test whether space-time behaves as general relativity predicts, or whether modifications are needed. If acceleration requires modified gravity rather than dark energy, gravitational waves should reveal the difference. Early results support general relativity and dark energy, but the field is young. More detections, more precise measurements, more sophisticated analysis, all might eventually reveal what dark energy truly is. What we've discovered is humbling. The universe is mostly invisible, mostly mysterious, mostly composed of things we cannot see and do not understand. Normal matter, everything we've ever touched, observed, studied, is a minority constituent, less than 5% of cosmic contents. The rest remains hidden, known only through indirect effects, waiting for insights that might come next year, or might require physics we won't develop for centuries. Deeper questions remain. Does dark matter interact with itself through unknown forces? Does dark energy vary over time or space? Are dark matter and dark energy related, aspects of some deeper physics? The universe operates on principles we're only beginning to glimpse, built from components we cannot directly observe, controlled by forces we've only recently discovered exist. What we've learned makes clear how much remains unknown. The invisible universe surrounds us, shapes everything we see, and guards its secrets carefully. Our Sun has 5 billion years of hydrogen fuel remaining before its core contracts and heats, triggering helium fusion in a shell around the inert carbon core. This is not a gradual transition, but a dramatic transformation. The Sun swells into a red giant, its radius expanding 100 times, its surface reaching Earth's current orbit. Mercury and Venus vaporize completely, their atoms dispersing into the solar wind. Earth might survive just barely at the outer edge of the expanded Sun's photosphere, or it might spiral inward through atmospheric drag and be consumed. Either way, Earth dies long before the Sun reaches it. As the Sun brightens over the next billion years, a natural consequence of increasing helium in its core, surface temperatures on Earth will rise. Oceans evaporate. The atmosphere becomes thick with water vapor, creating a runaway greenhouse effect. Surface temperatures reach several hundred degrees Celsius. Rocks melt. Any remaining life boils away. Earth becomes Venus, a scorched, sterile hell world orbiting a dying star. The final sunset lasts millions of years. As the Sun expands, it cools surface temperature, dropping from 6,000 degrees to 3,000 degrees, changing from yellow to red. Earth, if it still exists, experiences lengthening twilight, the Sun growing enormous in the sky, filling half the horizon, its dim red light barely illuminating the molten surface. Eventually, the photosphere engulfs Earth's orbit. The planet, already dead for billions of years, finally ends as scattered atoms in the Sun's outer layers. The Sun then sheds its outer layers through stellar winds and periodic ejections, creating a planetary nebula, a cosmic flower blooming for 10,000 years before fading. The nebula's gases, enriched with carbon and oxygen forged in the Sun's core, will disperse into space, eventually joining molecular clouds where future stars will form. The Sun's atoms, once part of previous stellar generations, will become part of new stars, new planets, perhaps new worlds where new life arises billions of years hence. Left behind is a white dwarf, the Sun's exposed core, the size of Earth but weighing 600,000 times more. A teaspoon of white dwarf matter weighs 15 tons. The Sun's entire mass, compressed into Earth's volume, supported not by fusion or gas pressure, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same state, creating pressure that resists further collapse. The white dwarf begins at 100,000 degrees Celsius, still glowing from residual heat, shining white-hot in the darkness. But it produces no new energy. No fusion occurs in its carbon-oxygen core. It simply radiates away stored heat, cooling slowly over trillions of years, fading from white to yellow to red to finally black, a black dwarf, a cold stellar corpse drifting through space forever. How long does cooling take? 10 billion years to fade to red, 100 billion years to become nearly invisible, 10 trillion years to reach near absolute zero temperatures. But forever is much longer than trillions of years. The universe is currently 13.8 billion years old. White dwarfs have existed for perhaps 12 billion years. None have had time to cool to black dwarfs yet. Every white dwarf still glows, still radiates, still marks the grave of a star that died billions of years ago. The universe's far future stretches beyond comprehension. In 100 trillion years, the last red dwarf stars, small, cool stars that burn hydrogen slowly, will exhaust their fuel and fade. Star formation will have ceased long before. In 40 trillion years, gas clouds will have been consumed or ejected from galaxies. No new stars form. The stelliferous era, the age of stars, ends. Galaxies go dark. What remains? White dwarfs cooling slowly. Neutron stars, collapsed cores of massive stars, 15 miles across, spinning hundreds of times per second. Their surfaces harder than diamond, their magnetic fields trillions of times stronger than Earth's. Brown dwarfs, failed stars too small to ignite fusion, radiating faint infrared heat as they contract. Black holes, stellar mass monsters created from collapsed massive stars, and supermassive behemoths at galaxy centers, consuming any matter unlucky enough to drift too close. The universe enters its degenerate era, lasting from 100 trillion years to perhaps 10 to the 40th power years. During this incomprehensibly long age, white dwarfs cool, brown dwarfs fade, and occasional collisions between stellar remnants create brief flashes of light, perhaps the last natural light the universe will ever produce. Planets still orbit dead stars, though most have been ejected through gravitational interactions over the trillions of years. Galaxies, held together by dark matter halos, persist as collections of dark objects moving through darkness. But even this isn't the end. In 10 to the 36th years, white dwarfs begin colliding through random gravitational encounters, occasionally achieving mass above the Chandrasekhar limit 1.4 solar masses, the maximum mass electron degeneracy pressure can support. When this threshold is exceeded, the white dwarf collapses in less than a second, compressing carbon and oxygen to nuclear densities, triggering a runaway fusion reaction. The star explodes as a Type Ia supernova, the same stellar explosion we use as cosmic distance indicators, briefly illuminating the dead universe with the power of 5 billion suns. These collisions become increasingly rare as white dwarfs spread apart through dark energy's continued acceleration. But in the unimaginable expanses of time ahead, rare events still occur countless times. Dead galaxies occasionally collide, their white dwarfs passing like ghosts through each other, occasionally interacting gravitationally, very rarely colliding. Each collision creates a brief moment of brilliance in the eternal dark. Black holes dominate from 10 to the 40th to 10 to the 100th power years. These gravitational monsters, ranging from stellar mass to billions of solar masses, persist longer than anything else. They consume stray matter occasionally, briefly illuminating as accretion disks form, but mostly they simply exist, warping space-time around them, growing slowly through rare captures, patiently waiting in darkness. But even black holes die. In 1974, Stephen Hawking discovered that black holes emit radiation through quantum effects at their event horizons. Virtual particle pairs constantly appear near the horizon. Normally, both particles annihilate immediately, but near the event horizon, one particle sometimes falls in while the other escapes. The escaping particle becomes real, carrying away energy. The black hole loses mass, it evaporates. The process is extraordinarily slow. A black hole with our Sun's mass 8 stellar mass black hole, typical of those formed from collapsed stars, would take 10 to the 67th power years to evaporate completely. That's 10,000 trillion years. Writing out this number requires more zeros than there are atoms in the observable universe. Yet it's finite. Given enough time, it happens. Supermassive black holes take even longer. A billion solar mass black hole, like those at large galaxy centers, requires 10 to the 98th power years to evaporate. The universe is currently 0.0000001% through this process. Yet eventually, it completes. The black hole shrinks, its Hawking radiation increasing as it grows smaller, finally exploding in a burst of gamma rays in its final second. What remains after the black holes evaporate? Photons like particles stretched to radio wavelengths by cosmic expansion, neutrinos, ghost particles that barely interact with anything, left over from earlier eras, electrons and positrons occasionally created by photon collisions in the dilute radiation field. The universe becomes a thin soup of particles and radiation, spread across unimaginable volumes, cooled to temperatures indistinguishable from absolute zero. This is the heat-death maximum entropy, minimum energy gradients, thermal equilibrium across all space. No stars shine, no black holes persist, No structures exist, just particles drifting through expanding space forever, their interactions so rare that billions of years pass between events in any given region. Time becomes meaningless because nothing changes. The universe reaches its ultimate state and remains there eternally. Or does it? Quantum mechanics suggests otherwise. Even in heat death, quantum fluctuations occur, random variations in energy and particle positions arising from Heisenberg's uncertainty principle. Most fluctuations are tiny, insignificant. But given infinite time, large fluctuations must eventually occur. Fluctuations large enough to create matter, large enough to create structures, large enough perhaps to create new Big Bangs. The timescales defy comprehension. Poincaré recurrence time. How long before quantum fluctuations randomly reassemble particles into their current configuration is estimated at 10 to the 10 to the 68 power years for a small region of space. For the entire observable universe to randomly reconfigure into its present state requires 10 to the 10 to the 120 power years. These numbers are so vast that calling them large understates their scale by factors that themselves require exponential notation to express. Yet they're finite. Given truly infinite time, they will happen. The universe might spontaneously fluctuate into a new Big Bang, creating a new space-time bubble that expands and evolves, eventually producing galaxies, stars, planets, perhaps even life and consciousness again. This new universe might have different physical constants, different laws of physics, different possibilities for structure and complexity. Some theories suggest our universe is one bubble in an eternal multiverse, where quantum fluctuations in the far future 10 to the 10 to the 56th power years hence constantly trigger new Big Bangs. Each bubble universe evolves independently, experiencing its own history, its own structure formation, its own eventual heat, death, or big rip, or big crunch. The multiverse persists eternally, constantly creating new universes, an endless cosmic cycle transcending individual universe lifetimes. Other theories propose cyclical cosmology, the universe expanding and contracting eternally. Each Big Bang followed by expansion, eventual recollapse into a big crunch, and bounce into a new Big Bang. Each cycle might be identical, or each might differ slightly, physical constants varying from one cycle to the next. We might be in the trillionth cycle, or the first, with no way to determine which. Or perhaps dark energy strengthens over time, creating phantom energy that accelerates expansion ever faster. In perhaps 20 billion years, not trillions but billions, just slightly longer than the universe's current age, acceleration becomes so intense that it overcomes all forces. Galaxy clusters tear apart first, their members accelerating away faster than gravity can hold them. Then galaxies themselves rip apart, their stars flung into isolation. Then solar systems disintegrate, planets stripped from their suns. Then planets themselves shred, rocks torn apart by space-time expansion. Finally, atoms themselves cannot hold together against accelerating expansion. Electrons rip away from nuclei. Nuclei disintegrate into individual protons and neutrons. Perhaps even protons and neutrons dissolve into quarks. Space-time tears itself apart in the Big Rip expansion, reaching infinite rate in finite time, ending the universe not with a whimper, but a catastrophic shredding of reality itself. Which future awaits? We don't know. The universe's fate depends on dark energy's nature, which remains mysterious. Observations currently suggest dark energy remains constant, leading to eternal expansion and eventual heat death. But we've only observed dark energy for a cosmic instant the past few billion years of the universe's 13.8 billion year history. Extrapolating this behavior, trillions, or billions of trillions of years into the future, requires assumptions we cannot verify. The atoms in our bodies have existed for billions of years, forged in stellar furnaces that died before our sun was born. Carbon, oxygen, nitrogen, calcium, iron, all created through nuclear fusion in massive stars, scattered through space by supernovae, assembled into new solar systems, eventually becoming part of planets and life. We are literally made of stardust, our atoms billions of years old, recycled through multiple stellar generations. These atoms will outlast Earth, outlast the Sun, outlast the Milky Way. After the Sun becomes a white dwarf, after Earth has been vaporized or consumed, your atoms will drift through space. Some might join new molecular clouds, becoming part of future stars and planets. Some might fall into black holes, compressed beyond recognition. Some might drift through intergalactic space for trillions of years, lonely travelers through eternal darkness. In the far future, some of your atoms might be part of the last generation of stars, shining in the twilight of the stelliferous era. Others might spend eons as part of a white dwarf, slowly cooling through the degenerate era. A few might survive to the black hole era, orbiting stellar remnants or drifting through the emptying universe. Perhaps, in the unimaginably distant future, they'll participate in quantum fluctuations that create new Big Bangs, entering new universes with new physical laws, experiencing realities we cannot conceive. We are temporary arrangements of ancient matter, brief moments of consciousness in matter's eternal journey. For a cosmic instant, these atoms organize into patterns complex enough to wonder about themselves, to look out at the universe, to ask questions about beginning and ending. Then the patterns dissolve, but the atoms persist, continuing their journey through time. This is both humbling and profound. We are not separate from the universe, but part of it. Atoms that briefly achieve consciousness, star stuff, contemplating stars, the universe's way of understanding itself. Our existence spans perhaps 80 years in a universe aged 13.8 billion years, existing on a planet orbiting an ordinary star in one galaxy among hundreds of billions. Yet through science and reason, we've decoded cosmic history, traced our atomic ancestry to stellar furnaces, and projected the universe's fate across timescales exceeding comprehension. What we've discovered reveals a universe more ancient, more vast, more strange than anyone imagined. A universe that began in fire and will end in ice, or perhaps in new fire, new beginnings, eternal cycles we cannot yet prove or disprove. A universe where endings are always temporary arrangements of matter, transitioning to new configurations, where nothing truly disappears but only transforms, where the journey continues long after any individual traveler has concluded their part. The final chapter hasn't been written yet. It won't be written for trillions of years, or perhaps never, if cycles continue eternally. We witness one brief moment in an incomprehensibly long story. 13.8 billion years in the telling, with an infinity or something approaching infinity yet to unfold. Time will achieve ultimate victory, yes, but the victory might not be an ending. It might be a transformation, a transition, a doorway to futures we cannot imagine from physics we don't yet understand. The universe began in mystery, the Planck epoch, inflation, the matter-antimatter asymmetry, and it will end in mystery. Its final fate depending on dark energy we cannot explain, on quantum fluctuations we cannot predict, on timescales we cannot comprehend. Between beginning and end, structures form and dissolve, matter organizes into complexity and disperses into simplicity. Consciousness arises and fades. We are witnesses to a story without true beginning or end, participants in a cosmic drama playing out, across scales of time and space that dwarf our individual existence, yet depend on us, depend on conscious beings, somewhere, somewhen, to observe, understand, and give it meaning. This is the final chapter as far as we can see, but deeper truths remain hidden beyond our current vision, waiting for insights we haven't yet achieved. depending on observations we haven't yet made, revealing mysteries we haven't yet imagined. The universe's ending, like its beginning, lies just beyond our reach, knowable in principle, mysterious in detail, beckoning us forward to discover what comes next.